Hello, everyone. So yes, I'm Steve Babbage from Vodafone. Very nice for me to be speaking here as the Group 2 tour already heard. I have an emotional attachment to this place because this is where my father spent the war as a crypt analyst in Hut 6. So I'm going to be talking about security for mobile things, and by mobile things, I mainly mean things with something like a cellular connection today, so a wide area connection, not so much like Mike's doorbell, which has a Bluetooth connection to something with an onward wide area connection, but things with built-in wide area capabilities. I'm going to be talking about the security aspects that I think the mobile industry is responsible for, which is not every single aspect of IoT security. What that security looks like today for mobile things, where the keys come from and how is such an important part of this story, and it's a challenging part, how I think all this is going to have to change for the Internet of Things, and specifically how provisioning, I think, will have to change for the Internet of Things. So, Internet of Things, first of all, this is a point that's come up. So I'll be referring back, by the way, there are quite a few things from previous talks that have sort of set me up nicely here. I think I'll also be disagreeing in quite a few respects with our previous speaker, so that'll be interesting. Have some conversations to have afterwards. This isn't my picture of the Internet of Things, it's just one I found on the internet, but for me it raises questions of how much of an internet it really is. So, does my light bulb really need to talk to my coffee machine? Does my tap really need to talk to a lorry? I want to say, does my smartphone really need to talk to a cow? But actually, if I'm a farmer, maybe it does. So that's not the most stupid link on this picture. But even if it does, or even whether it is a legitimate reason, say I'm in logistics or something, and this app that wants to talk to one of the trucks in my fleet, it's still not going to talk directly to one of the trucks in my fleet. At least this is the way it generally looks today. My phone will instead be talking to an application server somewhere, which will then in turn be talking through some routing mechanism, mobile in our case, to reach the truck there. So whatever the Internet of Things device is, the little tracker or whatever on this lorry, it probably, in my opinion, doesn't need a publicly addressable, a public IP address that anything can get to. It's actually, this is the connection that needs to be made, and then it's a matter of local system arrangement, how these two things talk to each other. So I think this is probably my first point of disagreement with what Mike was saying in the previous talk. So I question how much of an internet this really is, but we'll move on to that. Move on from that, sorry. This is the kind of picture I'm going to be talking about. So typically, we will have whatever kind of device this is here. We've got a bunch of different possibilities here. In our mobile case, be talking over a radio link to a mobile base station or something like a mobile base station. Onward through mobile network, you may get a concept of what we call home network and visited network. So for instance, I'm a Vodafone UK subscriber, but when I go to France, I will have a home network of Vodafone UK, but a visited network that's helping me get that service, which will be whichever French network I've roamed onto. So this may be a bit of home network here, this may be a bit of visited network here. And then you've got an application server that is somehow related to the truck or the bin or the meter or whatever it is. In terms of attack surface, there are lots of different places where this system end-to-end can be attacked. The two little devils on this picture are where essentially IT system bits can be attacked. I'm not really going to focus on that in this talk. They're clearly very important, to get right. Someone hacks into the application server here where all the data from this thing is stored, then it doesn't matter how good your communication security part has been if the data in the server can be hacked in the first place. But that's outside the scope, I think, of the mobile part. This, of course, is very much in the scope of the mobile part, but it is basically IT security that we need to look out for. I'm not also going to be talking about attacks, physical attacks against the device itself. I think that is a very important part of the end-to-end picture, but it's not what I'm going to be dealing with. These attacks may be trying to extract keys, which could be communication security keys, or they could be directly trying to extract data or subvert the functionality of the device or whatever. But the main points I'm going to be talking about are the communication security parts of this picture, which are these two devils here, the radio interface communication and the internet communication, essentially. This bit is what is generally within the scope, the remit of the mobile operator, and this radio communication part, of course. Over here, this is typically going to be one of our customers. So I'm going to do a quick explanation for those of you who don't know it already of what mobile security looks like. I'm just going to do the picture for GSM. I'm not going to go through all the variants for different technologies. This is more about phones than about cellular devices, than about IoT devices, but you kind of need the basic picture here as a jumping off point for what I'm going to be talking about. So we had this home and visited network concept that I already mentioned. You've got the phone. You can see how old this slide is, how long I've been using it for from what that phone looks like. And you've got the SIM inside the phone. So it gets a little bit technical, but just bear with me on all this. So in the home network, we've got AKA stands here for Authentication and Key Agreement. It's a cryptographic algorithm. When I need to authenticate to the network, two things feed into this algorithm. There is this, which is a secret key, and you'll see in a minute that this secret key is shared between this node and my SIM, and it's unique to my SIM. And then as a one-off thing, you've got a random number that's generated. That's the variable input to this algorithm. Then two things come out. Think of the random bit as a challenge, the challenge saying, prove you have the key. This is an expected response to that challenge, and this KC is going to be a cipher key that's going to be used for encryption, like a session key. The challenge, expected response, and cipher key are sent from the home network to the visited network, and the challenge is then sent over the radio interface to my phone that passes it to my SIM. We've got the same crypto algorithm and the same key here. Same random challenge goes in, same two results come out. So the res, that's the response, should be the same as the expected response. The response is passed to the phone, which sends it back over the radio link. The visited network compares, is the response indeed the same as I was expecting? If it is, then I have proved knowledge of this key without actually revealing the key. So that's authentication successful. And then I've got this KC cipher key. That's also passed from the SIM to the phone. Now that we've got this KC shared between phone and visited network, so we can use that for encryption on the radio link. So this is the basic picture in GSM security. If you go on to 3G and 4G, it kind of elaborates on this a bit. You get stronger algorithms, longer keys, a few extra components that mean you get authentication of network to device as well as device to network. But the basic picture is somewhat similar. So bear this kind of picture in mind as I go on with the talk. Just to pick out two algorithms here. So you've got the authentication and key agreement algorithm there and the radio interface encryption algorithm here. So back to the picture now. Where does encryption happen in the mobile network? Well, I showed you where it happens. It happens between the mobile device and the visited network, which is great because this radio part is the really exposed part, you may say. And certainly in the kind of phone world, that's pretty much is the most exposed part. But in this picture, we've got communication that's ending up on an application server that's somewhere on the internet. So it's clearly not enough just to encrypt this radio part. Moreover, this radio part, in many cases for what we call machine-to-machine devices, it is 2G because 2G has the widest, deepest coverage. And I don't want to pretend otherwise. 2G security is better than nothing, but it is not fabulous. 3G and 4G security are much better than 2G. So clearly, this is not enough. And so in practice, for services that need serious security, at the moment, they run end-to-end encryption, use something that's pretty much independent of our network, and that's absolutely the right thing for them to be doing. Now, in the mobile world, I showed you where the radio interface encryption keys come from. The radio interface encryption keys are the green ones, they're session keys, and they are generated from a long-lived key that's shared between the SIM here and a secure element in this home network, which is called the Authentication Center. So that's where the green keys come from. What about the blue keys? Where do they come from? Well, it's generally not done by us. It's done by the customer and or device manufacturer. But as Kenny talked about earlier on this morning, this is something where actually where the keys come from bit is really quite a challenging question. If the keys have to be put in manually by some technician, that can be a huge logistical overhead, and many of these devices probably won't have a natural interface for that to happen anyway. If they're all programmed in a factory, then it's quite hard to do that well. Factory provision keys, you'll typically often end up with same keys being used many times, or you may just end up with a factory that is not naturally a secure processing environment. If it's a factory where little location devices are made, or where gas meters are made, or where dustbins are made, or whatever, it's not obvious that that's going to be a secure environment that's immune from hacking and that is good at doing a good security job. So one possibility that we're moving towards today in our own service to customers is to have the end-to-end keys provided with provisioned with our help based on SIM keys. I'm not going to go into too much detail about this. There's a protocol called generic bootstrapping architecture, which if you're really interested, you can go and read up about, but I'm not going to start talking about now. But it's a way of deriving application level keys or transport level keys from the basic mobile connectivity security keys. And it's probably a pretty good way of giving a decent level of security of the provisioning process in a very convenient way to customers. Now, that's all kind of where we are today or pretty soon after today. But one of the big research and development areas for us at the moment is what we're calling the cellular Internet of Things, which is trying to build on where we are with mobile networks today, but achieve a great deal more for the Internet of Things. So a much bigger communications, a much bigger reach, I suppose, is the right term to use here. So 20 dB's additional link budget to reach way out into remote areas where you wouldn't be able to get a mobile signal today, deep into basements where you wouldn't be able to get a mobile signal today, but is precisely where things like smart meters need to go. In many cases, we've heard this referred to before, battery lifetimes, so devices with a single battery that will have to last maybe 15 years on a single battery. Extremely low-cost devices. We're trying to enable the billions of devices here. We've got a very healthy machine business today, but it won't be able to reach the sort of $2 devices that will work deep in a basement. We are trying to build this as an evolution of the current mobile system. There are commercial networks as well that are trying to build essentially new networks in parallel separately from the 3GPP tracks. We may well have representatives of some of those networks today, but we're trying to do this on the basis of the very widely rolled out 3GPP-based 2G, 3G, 4G networks that we have already. So, battery efficiency is going to be one of the key issues for this. So, where are we going to do the encryption? Today, I said that where security really matters, it tends to be done end-to-end. Now, the studies that people are doing in 3GPP at the moment on battery life, if you want a battery, in a smallish battery in a device that's going to keep it going for 15 years, the biggest drain of all on batteries is radio transmission for mobile devices. Computation matters, reception of radio transmission matters, but more than anything, outward transmission is what drains the battery. End-to-end security protocols like TLS, DTLS, there's a big overhead in those. The studies that people are doing in 3GPP are suggesting that for a device to last 15 years, you could maybe afford 20 bytes a day for security. Now, if you're going to send 1 byte of information a day, or a couple of bytes of information, which a sensor might do, but then you've got a huge packet or security association set up overhead every time you do that, that's your battery gone. It's not going to last you your 15 years. So this is, again, a point of disagreement with the previous talk, so I'm looking forward to having this discussion. So an alternative is to say, well, we have the existing radio interface encryption here now, but I already said this is clearly not enough. Even if you have excellent security here, you've got a whole internet here. You can set up VPNs here. So there's another possibility here. You don't have to have the internet exposed. You don't necessarily need per device security association, security tunnels here. But you've got a bit of exposure here as well between home network, visited network, international signaling, and so on. It's not a fantastic end-to-end security proposition to our customers if they have high security requirements to rely on radio interface encryption plus maybe a VPN. So the model that we think can work is one where mobile security is rethought to work from the device into the home network, and then something like VPN onwards here. Now, this is a different way of doing mobile security. It's not something that's standardized yet. These are ideas we are currently taking into the 3GPP standards. They raise questions to do with lawful interception. If at the moment where encryption only terminates in the visited network, if there is a lawful interception warrant, it's easy to apply that warrant somewhere in that visited network. That may become less straightforward if you're encrypting all the way into the home network. I think it raises some interesting questions. My understanding is that the exact requirements for legal intercept on cellular, on IoT devices are still really being hammered out. If I've got time at the end of my talk, I may say a little bit more about that, but I'll move on. I'll move on for now, and then you can tell me whether I've overrun or underrun. Now, one of the things to consider for security is how often to create new session keys and how to do that. So it's pretty well established that from security point of view, if you're going to be using a session key, you don't really want to use the same encryption key indefinitely. That's pretty bad practice. You want session keys that get replaced. What drives the need to do that? Well, really, there are two reasons why you need to update keys with a certain frequency. That can be based on the volume of data you are encrypting, or it can be based on the length of time that the session key may be exposed for. Now, in the case of this cellular Internet of Things, probably the volumes of data are really small, so that's a minor consideration. It's the length of time that the key is exposed for that is really the big consideration here. And remember, back to the GSM security picture I showed you, the long-lived key, the one that was called KI, that's stored in the SIM and never leaves it, and the SIM is pretty good at keeping secrets. The session key, however, is passed from the SIM into the phone, which is a much more exposed hackable environment. And the session, the long-lived key sits in a secure component in the home network. The session key will typically be in a more sort of communications operational part of that network. So maybe somewhat more exposed. I'm not going to say, clearly in both those cases you do your best to keep them secret, but it's not as high security as the authentication center in the network. It's not as high security as the SIM. So, this is my authentication center in pretty big brick wall here, and here's the SIM. That's just what I was talking about already. So moving on from here, the operation in mobile of deriving session key from long-lived SIM key, I showed you already. It's an authentication and key agreement operation which bundles together actually two separate operations. There is the authentication part that proves that my SIM, it really is my SIM wanting to access the network now, and therefore it's correct to charge this call to my bill. And it is the key agreement part that creates session keys. Now, authentication is a moderately heavyweight cryptographic process, and you can't really do authentication with a couple of bytes of data. Key agreement, on the other hand, need not be such a heavyweight operation. So one of the ideas that we want to take from Vodafone into the standards is the idea of separating these two operations and introducing an intermediate level key so that you would still have your long-lived key here. Whenever you wanted to authenticate, you would create a new intermediate level key, and this is part of an authentication exchange with the network with as many bytes as are needed to do that well. But you do that much, much less frequently than any time you need a new, and this one is going to be kept back inside the SIM still. Whenever you need a new session key, that's done using a simple key derivation based on this and maybe just an incrementing counter. And here, so you could probably get away with just 1 or 2 bytes of data being exchanged between mobile device and network as a trigger, once they already share this intermediate key, to come up with a new session key. And so you can create new session keys. They are still tied into the authentication process, which is really important because authentication is an instantaneous thing. And it's no use at all if I allow authentication to happen and then the attacker just muscles in and takes over the authenticated connection. You have to extend the effect of the authentication for the duration of that connection, or else it doesn't serve its purpose. So you are still getting that here, but with much lighter weight, frequent key update operations. So you might, for instance, if you wanted to change the session key once a day, maybe you do an intermediate key generation once a year and a session key generation once a day. We haven't even taken this into standards yet, but it is the kind of innovation that we are looking at to try and achieve the really battery-efficient security that we think we need. So, looking at really low-cost devices, I've been talking about the SIM in my talk so far. What's this SIM going to look like, first of all? Well, in mobile today, this is the sort of SIM that we used to know, and you've seen it shrinking in more recent smartphone devices. There's just been a separate track. These are all standardized form factors for the SIM. A separate track has moved towards this machine form factor. It is still a SIM, but it's now a soldered inside the machine device SIM. This is well established now. Lots of machine devices have this. Benefits of it being soldered are, well, partly, there's no need for a removable SIM, and removable SIM it takes up a lot of space and all the interface to it does. But also for other environmental considerations, these machine SIMs can withstand much greater extremes of vibration in cars or extreme low and high temperatures and stuff like that. So this serves an extremely important purpose. More recently, we're seeing what's called the embedded SIM, or the embedded UICC, UICC being the term for the hardware platform the SIM runs on, which is, so one of the limitations of this soldered SIM is that a SIM traditionally has always been manufactured for an individual operator. So it's been manufactured, say, for Vodafone UK, which is fine for all of these removable SIMs. You just buy a phone, and then if you're a Vodafone customer, you plug in your SIM. For these, it means that the device has to be manufactured to be a Vodafone UK device when it comes out of the factory. So there is a soldered component in it that is Vodafone UK specific. That's not always what you want from a logistics point of view. You want to be able to churn devices off the factory floor where you don't even necessarily know what country they're going to end up in. So this embedded SIM is a more recent innovation that allows a kind of vanilla SIM to exist here. I mean, in practice, probably a soldered one in a machine device, but I've shown it here in a phone, and there's no reason why it can't apply in phones. You've seen very limited steps in this direction from Apple already last year. And there's plenty of work going on in GSMA on embedded SIM for mobile, for smartphones and tablets as well. But the big driver comes from machines, where you can have a vanilla SIM not particularly tied into a single operator here at manufacture, and then it's an over-the-air operation, secured over-the-air operation, that provides it the credential for its ultimate destination operator. So it can be turned from a vanilla SIM into a Vodafone UK SIM by secure over-the-air operations. So this is what machine SIMs are looking like today, and we've already got sort of steps in this direction today already. But think about the production costs of these. One of our drivers here is to move towards very, very low-cost devices. Now, the cost of a SIM is not just the cost of the hardware. It's also the processing cost. So you have a factory here where the SIM hardware with its operating system and so on is being created, but you need to provision unique identifier and key into that, and you really need to do that in a pretty secure place. And so the model today is that this may be created by a sort of chipset company like an Infineon or someone like this, but here you'll have a SIM vendor, a G&D, Gemalto, Overture, Morpho, these kind of companies, which are doing individual provisioning of keys and identities in a highly secure environment, which is terrific from a security point of view, but it's a pretty significant processing overhead to have. You can't just have these things churning off the factory floor. You could try to take out this extra step, but bear in mind that this then is probably not as high security an environment as here. So it's entirely possible you're going to get attacks on the factory floor. Some of you may be aware that we've had reported attacks here as well in the last few months. That's an interesting one. I won't try and catch anyone's eye in this audience, but we think there is maybe a way of achieving a happy compromise here, whereby, that hasn't come out terribly well on the slide, whereby keys are programmed in at the factory floor, but the only thing that they are used for is to provide a limited amount of authentication for an initial over-the-air key setup operation. So we're thinking about an authenticated end-to-end key exchange, something like a Diffie-Hellman key exchange or elliptic curve Diffie-Hellman key exchange, which would be a one-off process that will create new shared keys between the hardware here, whether you call this a SIM or not, and sorry, I've drawn this picture actually wrong, because this wouldn't be an operation between the SIM and the factory in which the hardware was made. That's missing the point completely. I need to rethink this slide. This will be an exchange between this hardware and an entity working on behalf of the mobile operator. And you can, I don't want to overcomplicate it. You can have multiple chains of key exchange to hand over from maybe one subscription management operating device, operating server that's associated with the device, followed by a second one that's associated with the mobile operator. I can go into far more detail offline if anyone's interested in this, but we think here you can reduce the processing cost of the manufacturing operation, but still end up with a pretty decent level of security, where it doesn't matter so much that you are using keys from here, but you don't have anywhere near the same ongoing reliance on their security. So, to come to a conclusion, we think design constraints require new thinking. You may even say new compromise, but we are working with some pretty extreme constraints. If you're designing purely from a security point of view, you certainly have end-to-end security from device to application server, but we don't believe you can afford that from a battery point of view here. So we think the best compromise is instead going to be that picture I showed you of a two-leg security, device to home cellular network and then cellular network to application server. We love the SIM, and we've had fabulous mileage from the SIM and its security over the years, but we think some kinds of compromise, some rethinking of that is going to be necessary for the really low-cost Internet of Things devices. But with thoughtful design, you can achieve good compromises which still give you good levels of security, we think good enough for the services necessary. So I saw differences. So Mike was talking more about kind of end-to-end TLS variants, whereas I was arguing here that I struggle to see how they can be made given low enough overheads. And he was talking more about, as he put it, IP to the edge, whereas the picture I drew right at the beginning was much more about a proprietary, but the IP pretty much terminating at the application server. Oh, sorry, not at the, well, yes, at the application server from the external world point of view. Separate IP connection, perhaps, obviously, connecting mobile network and application server going on. This may not meet every single requirement. I'm sure that there clearly are going to be more internet-y devices that you do want to expose in a bigger way, but our conjecture, and at least from most of these services we've provided to customers so far, don't really look like that. And we don't believe there's a need for end devices to have IP addresses that can be pinged from anywhere on the internet. Yes. So I mean, we're probably coming from it from different perspectives. I think if you were putting, let me be clear about this. You have trade-offs to make. There are drivers in terms of very low-cost devices and in terms of battery efficiency. There are drivers in terms of high security. You want to try and different services will have different requirements on that sort of 2-3-dimensional graph. There are some where the battery efficiency is an absolute given and you have to do the best security you can. There are some where really high security is a given, and if that means that you're not willing to contemplate an alternative to end-to-end security, then you cannot achieve the ultimate extremes of battery life. You have to find your best compromises. What we're trying to do here is reach what we think are good compromises using a bit of creative design that allows us to reach further into those more constrained device areas. So that is a good question. I think there are elements of this where, well, what I've been talking about, where having a single framework is fine. So for instance, whether you're using a SIM as we know it or some variant on the SIM, that can all function in the same way. It's sort of subsequent functionality that doesn't need to look different. But there is a pretty fundamental difference in approach between running something like DTLS or a cut-down DTLS and the encryption approach that I was talking about. So, well, I'm sure it's possible to define a framework to accommodate both. Framework is a pretty broad term, but you know, I think a one-size-fits-all way of doing security could be hard. So, something I think would help the industry as a whole is and this is something that John and Stan and I have had some conversations about, is a kind of agreed way of representing the whole sort of set of security requirements for a service, which will vary between services clearly, but looking at it kind of end to end, and then assessing how an end-to-end solution, or the components of that solution, meet those requirements. So I think a kind of a common language for talking about this would be a really useful step. I think it's part of what probably industry and government needs to get, A, a good understanding, but B, good confidence to progress. And I don't expect that it would typically be a single part of the solution would tick all the boxes. You know, I said, for instance, it wouldn't naturally be the mobile company, the mobile communications provider that would provide all your device security requirements. So you probably have to look at it from a kind of integrated solution point of view. Well, unless you're buying your whole solution from a system integrator, in which case I suppose they can do that for you. But so I don't know if I'm quite answering your question, but I think this is the sort of approach we need, a common way of talking about requirements and how well those requirements are met by different solutions.
We're going to have to move on to the next speakers here, but thank you very much for... Welcome.